Hey everyone! Today I'm diving into a fascinating topic, how satellites stay in orbit. Have you ever wondered how these man-made objects manage to float around our planet without falling back to Earth or drifting off into space? Well, you're in the right place. We're going to explore the science behind orbital velocity and the time period of satellites. These concepts are fundamental to understanding satellite motion. So, let's get started. First up, let's talk about the motion of a satellite. This motion is a result of a delicate balance of forces. Satellites move in orbits around celestial bodies like planets or moons due to the gravitational force exerted by those bodies. This gravitational pull is what keeps the satellite from flying off into space. Imagine it as a tug-of-war between gravity pulling the satellite towards the planet and the satellite's inertia pushing it out into space. This constant pull and push create a stable path for the satellite. This balance keeps the satellite in a stable orbit. If the forces were to change, the satellite could either crash into the planet or drift away into space. Now let's break down orbital velocity. This is a crucial concept for understanding how satellites maintain their orbits. Orbital velocity is the speed a satellite needs to stay in orbit around a planet without falling back to the surface. This speed ensures that the satellite's inertia perfectly counteracts the gravitational pull. This speed depends on the mass of the planet and the radius of the orbit. The formula to calculate orbital velocity, v, is v equals sinus sqrt, frac, gmr, where g is the gravitational constant, a value that represents the strength of gravity in the universe. M is the mass of the planet, which affects how strong its gravitational pull is. R is the radius of the orbit, which is the distance from the center of the planet to the satellite. This distance plays a key role in determining the necessary speed for orbit. So, for a satellite to stay in orbit, it has to travel at just the right speed. Not too fast, not too slow. This precise speed ensures the satellite remains in a stable orbit. Next, let's talk about the time period of a satellite. This is another important aspect of satellite motion. The time period is the time it takes for a satellite to complete one full orbit around the planet. This period can vary greatly depending on the satellite's orbit. The formula to calculate the time period, t, is, the symbols here have the same meanings as in the orbital velocity formula. Understanding these symbols is key to grasping the concept. In simpler terms, the time period depends on the size of the orbit and the mass of the planet. Larger orbits mean longer time periods. For example, satellites in higher orbits take longer to complete one orbit compared to those closer to the planet. This is because they have a larger distance to cover. The motion of satellites is a delicate dance of physics and gravity, ensuring they stay on their intended path while whizzing around Earth or other planets. This dance is a marvel of modern science. It's amazing how precise these calculations need to be to keep satellites in orbit. Even a small error can lead to significant deviations. So, the next time you look up at the night sky and see a satellite passing by, remember the incredible science that keeps it there. It's a testament to human ingenuity and our understanding of the universe. Thanks for tuning in. If you enjoyed this video, don't forget to like and subscribe for more cool science content. See you next time.